So I'm happy to present our today's speaker, Professor Muravnik from People Friendship University from Moscow, and his title would be the title on the screen. So if you're ready, then please, Professor Muravnik, please go ahead and thank you.
Thank you very much. I am pleased and proud to be the speaker today. Your seminar is a very famous event, well, regular event in the mathematical life of the whole world, let me say, at least in our research area, and this area is treated very broadly. So thank you very much again. Let me start from a few words about our mathematical direction. Recently, Professor Skubachevsky was the speaker at your seminar, and I belong to his mathematical school. But please do not try to seek too many similarities between his lecture and my one today, because definitely our research area is rather broad. But anyway, this the presentation that you see now is let me say in the line of the research interests and research advances and successes, if the word success has the plural in English, of Skubachevsky and his team and school. How can I change slides? Let me try. No. Okay, let me do this. I would like to start from certain remarks about the history of the problem. Today I will talk about functional differential equations and actually only about differential difference ones. Let me recall that if an equation includes not only differential operators, but other operators of another nature, then it is called, it is said to be a functional differential equation. It is definitely a very common, a very general object. Let us make it more narrow and consider only equations that okay, maybe a little bit later, sorry. So what is the reason to study functional differential equations as a separate research area? There are the following main reasons. First, we face qualitatively new phenomena not occurring in the classical theory of differential equations. Second, we see that a number of classical research methods that work in the theory of differential equations very well turn out to be inapplicable in the case of functional differential equations. And finally, there are many areas of applications not covered by the classical theory of differential equations, but functional differential equations turn out to be quite useful for those applications. I think I just must to mention the pioneering paper in this area. Definitely, roots of each more or less broad or general theory are quite questionable topic, and some researchers follow roots of the theory of functional differential equations, for example, until Euler. But in, let me say, in the contemporary mathematical landscape, we generally refer our readers or listeners to this pioneering work of Hartmann and Stampakia. Is my marker is the moving of my marker seen for you?
Yes, perfectly.
So I can use it as a pointer. Okay. Now we forget about functional differential equations as a whole and continue to discuss only differential difference equations. What are differential difference equations? They are equations containing, apart from differential operators, translation operators. What are the specific properties? Excuse me. It is divided between two slides. Okay, let it be so. First of all, translation operators are Fourier multipliers. Similarly to differential operators, of course, symbols are different, but anyway, each translation operator is a Fourier multiplier. Another specific property refers to the classical classification of equations, whatever it means. In the classical theory of partial differential equations, we have a very well-known classical definition. How to define which equation is elliptic, which equation is parabolic, and which equation is hyperbolic. When we pass to differential difference ones, we have to introduce those definitions again. And the terminology is not canonical yet, but at least within this lecture, it would be enough to treat this classification as follows. First, we have to define elliptic equations or elliptic operators. We define elliptic differential difference operators as follows. If the symbol of the operator is non-positive everywhere, then the operator is said to be elliptic. And then we can introduce parabolic and hyperbolic equations, for example, as follows. Excuse me, it's a little bit fast. Let this be a kind of blackboard. So if L is an elliptic differential difference operator, then it is natural to say that operator of this kind is parabolic, and each operator of this kind is hyperbolic. Now, I have to say that the general theory of elliptic differential difference, and even more broadly, elliptic functional difference, functional differential operators in bounded domains is developed very deeply and very well. It is enough just to provide you these four sources, but not only them, but the list of reference for all of them, and then the reader will have more or less reasonable picture of the theory in this direction. But today we will consider problems in unbounded domains and problems for parabolic equations. I have to mention two key papers of one my very important predecessor in this direction. This is Professor Rabinovich Vladimir Samuilovich. It is especially pleasant that he started his work in mathematics in Rostov, where our organizers are physically situated now. Well, I don't mean Professor Kravchenko, but anyway, even though your seminar is online, for us it is for the first time is related to Rostov, and Vladimir Rabinovich started his mathematics in Rostov. Now he works in Mexico. Well, I don't have to say too much, because I think many of you know him much better than me, but I know Vladimir Samuilovich as well. He considered differential difference equations in half spaces more than 40 years ago, but his results are related to generalized solutions, to solutions from weighted Sobolev spaces. Today, I would like to present you results concerning classical solutions, and I would like to explain what is the reason to concentrate on classical solutions. Main results provided to you today, that I expect to provide you today, refer to the so-called stabilization theory, and this stabilization theory in a great part consists of assertions explaining the behavior of solutions at low dimensional manifolds, even on lines. And you see that once you have to define a function on a manifold of dimension 1, line is a manifold of dimension 1, then the belonging of the solution to a Sobolev class might be not sufficient for this. But once we have a classical solution, then there is no problem to define its trace on each manifold of each dimension. So that is the reason to be interested in classical solutions. Let us start from, okay, I have to explain that when we consider differential difference equations, then it is reasonable to separately consider two big classes of such equation. One class is equations where differential operators and translation operators form sums. Another class is where differential operators and translation operators form superpositions. It is clear from various investigations, and they refer not only to equations of parabolic type. This phenomenon is faced in equations of all types, that for those two classes, we have qualitatively different results, so it is really reasonable to consider those classes separately. So first, let us start from the case where the equation contains sums of differential and translation operators. So consider the following Cauchy problem. Here, each hj is a vector, n-dimensional vector in this space. Each hj is orthogonal to another hj to another vector h with another index j. They are normed, and coefficients a jk and b jk are just real scalar coefficients. The initial value function is supposed to be continuous and bounded in Rn. So we consider this Cauchy problem. So you see the index j counts translation vectors, and the index k counts the number of non-local terms of the equation translated in the direction of each vector. The following results are obtained for this problem. Function 3, where E calligraphic of xt is defined by this relation, is the unique classical solution of problem 1, 2, bounded in each layer r to the power n times the segment 0 t capital, where t capital is positive. I prefer to provide the list of presented result first, and then to say a few words about ways to prove them, if the time will permit it. So the next result about problem 1, 2 needs a new definition. A differential difference operator acting in Rn is said to be strongly elliptic in Rn if there exists a positive C such that its symbol satisfies this inequality for each psi from Rn. Please note that the first assertion, the assertion about the unique solvability of our problem and the integral representation of its solution, needs no additional assumptions. But to say something about the asymptotical property of the solution, we have to assume something else. Now, theorem 2. Let this operator be strongly elliptic in Rn, where this symbol, L calligraphic, denotes this operator. And then the following limit relation holds for each x from Rn. This limit tends to infinity, where the function w of xt is the bounded solution of the Cauchy problem for the heat equation with this initial value function. And the constants p1, etc., pn, and q1, etc., qn, occurring in this assertion, are defined as follows. Please take into account that this condition of the strong ellipticity of this operator guarantees the non-negativity, of all these radicands. So under this assumption, the constants Pj are well defined. And I think this assertion should be illustrated a bit. I shall do it right now. So this is a theorem about asymptotical closeness of solutions. Let me recall you that such theorems are constructed as follows. We have a function that is to be investigated. We know nothing about this function. In our case, this is the function u of xt, more exactly u of xt weighted by something, but let me talk about this weight a little bit later. So we have an unknown function and we want to know something about its behavior. We have another function such that we know about it a lot. This is the solution of the Cauchy problem for the heat equation. And such function in assertion like this, in asymptotical closeness theorems, such functions are called echelon functions. And asymptotical closeness theorems say us that as t tends to 0, then the investigated function is close, quite close, yes, to this echelon function. And what is the difference between classical asymptotical closeness theorems and this theorem? Asymptotical closeness theorems arise in the parabolic theory, in the classical parabolic theory, very frequently. In many cases, stabilization theorems follow from them, and moreover, closeness theorems are stronger, because a stabilization theorem says us what happens with the solution if the stabilization condition is satisfied. It says nothing in the case where the stabilization condition is not satisfied, and therefore the echelon function does not have a limit. But the closeness theorem provides us an information even in the case where we have no stabilization. Look, W is an echelon function. We know about it a lot, so even if it has no limit, we still obtain a certain information about the function that is investigated. But in our case, we have the following qualitative difference. Look. Sorry, let this be our domain for the independent variable x, vector variable and dimensional variable. Let this be t. And what do we get from classical closeness theorems? We start from a certain point at the initial hyperplane, more exactly from an arbitrary point at the initial hyperplane. Then we tend t to infinity, yes, and the closeness theorems say us if the independent variable goes to infinity along this line, then the difference between the investigated function and the echelon function tends to 0. But in the differential difference case, picture is changed. We have the independent variable tends to infinity along this line in our echelon function, in our investigated function, and the independent variable tends to infinity along another line for our echelon function. And the angle between these two lines is completely determined by the set of these constants, and these constants are completely determined by the coefficients of the investigated equation. Everything about this refers to the weighted solution, but I have to explain why do we have this weight. Please look. If we destroy the non-locality, if we assign all coefficients at our translation vectors, all coefficients b, jk, to be equal to 0, then we obtain not the heat equation. We obtain the heat equation with a potential. And we know that in the classical case, when we disturb our heat equation by a potential, by a constant potential, and we have a constant potential if we set all our coefficients b equal to 0. So if we have such an equation, the heat equation with a potential, then the difference between its solution and the solution of the heat equation, I mean, in both cases, the solutions of the Cauchy problem, then the difference is the exponential, is a certain exponential factor. So in this case, if we would not have, excuse me, if we would not have non-local terms, then our W would have just one exponential factor. So now this is its analog, yes, and okay, let me write something at here as well. The one-dimensional case would be enough for the understanding. So if we consider the Cauchy problem for this equation, then it would have the following form: e to the power a t times u of x t, maybe up to the sign of a, excuse me, but nothing more. And you see, u is the bounded solution, the unique bounded solution of the Cauchy problem with the bounded initial value function u0. According to the maximum principle, it is bounded from above by the supremum of u0. Now, we add a potential and our solution gets outside the class of bounded function. But once we multiply it by the factor e to the power minus at, then our solution gets back to the class of bounded functions. The same take place in the differential difference case. We have an equation with potential terms, but they are non-local. So, no. Excuse me. We multiply the solution by an exponential term, and this gets this solution back to the class of bounded function. And for this weighted solution, we have the closeness theorem. Now, let us pass to the case of differential difference parabolic equations, where the equation contains superpositions of differential operators and translation operators. That is to the Cauchy problem with the same initial value function for equation 4. For the simplicity, E, J are unit vectors of unit coordinate vectors. AJK and BJK are scalar real coefficients again. Now we have to impose the strong ellipticity condition for the operator minus L from the beginning. And if this condition is satisfied, then function 3, let me recall you that this is the convolution of the kernel E calligraphic and the initial value function satisfies the Cauchy problem for equation 4 in the sense of generalized functions or distributions, if you like, and is a classical solution of equation 4 in the half space, in this half space. And there are no other solutions of problem 4.2 in the sense of generalized functions. And the kernel of this convolution, we may call it the Poissonian kernel. And this kernel is expressed this way. Still under the condition of the strong ellipticity of the operator minus L, we have the following assertion about the long time behavior of this solution. Theorem 4. If the assumptions of theorem 3 are satisfied, then this limit is equal to 0 for each x from Rn, where v of xt, this sign is not needed, excuse me, where v of xt is the bounded solution of the Cauchy problem for this equation with the same initial function u0 of x, where each pk is the sum of these coefficients. Note that the parabolicity of this differential equation, it is already a differential equation, not functional difference, not differential difference equation, and its parabolicity is guaranteed by the strong ellipticity condition for the operator minus L. So this case looks even simpler. Now I still have several minutes to talk a bit about the proofs. Definitely about main ideas lying in the base of proofs. Well, definitely to prove the solvability theorems, we can just take this integral, prove that it is well defined, prove that the differentiating inside the integral is legible, and substitute it into the equation. But this is a wrong way to explain something, because it's like I take a hat and extract a rabbit from it. I have to explain how do we find function 3. More exactly, how do we find the Poissonian kernel? Let me try to do it. We formally apply the Fourier transformation with respect to the n-dimensional variable x to the original problem. Why do I say formally? Because once I apply a Fourier transformation, I have to count an improper integral. So I have to prove that it exists, etc. I do nothing like this. I apply it formally and use the fact that differential operators and translation operators are Fourier multipliers. What do I get? We had a partial differential difference equation. Now we obtain an ordinary differential equation, and we get a Cauchy problem for it. This is a second order, excuse me, this is a first order ordinary equation, and its coefficients are constants. Xi is just a complex parameter, a vector parameter of the problem. So we can easily solve the Cauchy problem for this equation. Okay, once we do it, then we formally apply the inverse transformation, and we get our function 3. Let me not get back to this function, and just let me recall you that this is the convolution of our function e calligraphic with the initial value function. Once we do this, we have our function e calligraphic. And now we have to justify all the previous actions. That is, we have to do the following. In this we have to prove that our function 3, let me recall you again that this is the convolution of our function equally graphic with the initial value function of the problem. So we have to prove that this convolution is well defined in this half space. P, it satisfies in the classical function the original equation in this half space. It satisfies in the classical sense. And that convolution 3 is excuse me. A and B refers not to the convolution but to the kernel. And once we have A and B, then we have to prove that the convolution is well defined in this half space and admits the differentiating inside the integral. Actually, we have to clarify only the last item. What do we do? For each fixed positive t, we have to prove a sufficiently fast decay of the kernel and its corresponding derivatives as the absolute value of x tends to infinity. Let us show how we do this for the case where the equation contains sums of differential and difference operators. In the one-dimensional case, we decompose our kernel into its even and odd summands and reduce each of these summands to the following form, to the form 5, where f is an essentially bounded function, and psi is a summable function. And then we apply the following corollary from the Wiener-Tauberen theorem. The last integral tends to 0 as x tends to 0 if there exists a function psi 0 from L1 such that its Mellin transform is defined on the whole real axis and has no real zeros. And this limit relation is satisfied for our function psi 0. Look, this assumption about the Mellin transform is assumed only on the function psi 0. The function psi is to belong to L1 and nothing else. This follows from the Wiener-Tauberen theorem. And in our case, this function can be taken as 0 as psi 0 for both summands, both for the even one and the odd one. We can explicitly check that all our assumptions are satisfied for it, and then we prove that this function, the kernel, decays sufficiently fast. But we have to prove that the kernel decays sufficiently fast. Okay, not sufficiently fast. That the kernel tends to infinity, to 0 at infinity. But to prove that it decays sufficiently fast to be integrated, we have to prove that this function tends to 0 as x tends to infinity. To do this, we integrate it by part. We integrate the kernel by parts and reduce this product that we investigate to form 5 again. And repeating this procedure for its corresponding derivatives, we complete the proof of this item. This is done for n is equal to 1. If our spatial variable is multidimensional, then this way does not work intermediately. But we use the presence of special directions of the problem. They are determined by translation vectors contained in the equation, and apply the iterated decomposition into plane waves. What is amazing, at least for me, that usually we decompose into plane waves in hyperbolic problems. In this case, it works in the parabolic problem. But this yields us the following picture. We select a factor inside the integral coinciding with the function E calligraphic of our one-dimensional problem. And then we apply the result applied for the one-dimensional case. For equations with superpositions of of differential and difference operators, the problem is even easier. The integrand always contains this factor bounded from above by a function of this kind due to the strong ellipticity condition. The uniqueness proof is not interesting. We just base on our on results of many our predecessors. And to prove the result on the asymptotical behavior of the solution, we represent the investigated solution in this form, and the echelon function is represented in this form. And the difference that has to be estimated is represented by this form, by this sum, and then we just decompose the integral into its large and small parts. So we select the factor just our kernel in the integrand function, and we select it in the following way. The summability of the kernel and the boundedness of the remained factor is used in this summand, and the boundedness of the kernel and the limiting properties of the remained factor are used in this summand. This is a very well-known technique, and I don't think maybe it is interesting to show in details how does it work in this particular case, but I am sure that I have not time for this. So let me stop at this point, and thank you very much for your attention.
Well, thank you very much, Professor Muravnik, for a very nice presentation, and we have time for questions, if any. Maybe I'll have a small question. Meanwhile, I understand that you cannot use the Tauberian type theorem for multidimensional situation, but if you work with Fourier transform, maybe I'm wrong, but maybe you may use the theorems about Wiener ring, like that give you kind of sufficient conditions from you can just judge from the behavior of the image, Fourier image, you can judge about the pre-image. Maybe it's not sufficient for you, I'm not sure.
Thank you very much for the idea. I just can't say that I know something about Wiener rings, so I shall I shall look for them in the literature, and perhaps it might have a sense.
You see, a big review paper was published by Samko with a co-author exactly in Vestnik People Friendship University.
Really? Wiener rings?
Yeah. In 1991, I guess. A big review paper. Yeah.
In 1991?
1991, yes, more or less.
Ah,
yes.
I see.
It was Vestnik of Ruden.
Thank you. I even did not know that Vestnik of Ruden is so old journal. More than 30 years.
Maybe even 89, maybe even 89, I'm not sure. But I guess it's around
Anyway,
80s.
it's very old.
90s,
the
90s,
previous
I'm
century.
sorry. 90s,
Previous century.
yeah.
Okay, Wiener
Yeah.
rings.
But it contains a lot of sufficient conditions for functions to be
in the multidimensional
multidimensional case.
Yes,
Yes, of course, yes.
This might
It
be
uses fractional derivatives, integral
this
conditions, many. Yeah.
This might be very interesting because you see, we succeeded to prove the theorem in multidimensional case, but there are open questions. They are in the elliptic theory. I cannot say everything in one lecture. And in the elliptic theory, the multidimensional case is still open. So
Yeah.
maybe it might be useful. Thank you.
So the authors were Samko and Kosteckaia. If you don't find this paper, I can ask Kosteckaia. She will send. I hope I had this paper, but I probably cannot find it now.
Well,
but if you don't succeed to find it, I can send it to you.
Yes, I think being situated in Ruden University,
yeah, you will find it in the library.
Yes.
Yeah. But by the way, Vestnik Ruden, it doesn't exist now.
I'm not sure. Maybe it exists, but it is definitely not indexed.
Yeah, I see.
Okay. And in our current clinical situation, what is not indexed does not exist.
Okay.
It's a joke.
Yeah, I'm just trying to remember. Maybe maybe some co-published one more review paper later. If I find it, I'll send to you.
Thank you. Okay. Keywords Wiener rings are enough for a thorough search.
I don't remember the exact title of the paper, but it was kind of conditions for Wiener. Oh, I don't remember really.
Well, in any case, the term Wiener ring should be searchable.
Yeah. But you can search by authors, Samko and Kosteckaia.
Yes, definitely. Yeah. Thank you.
Okay, more questions, please. Well, if you don't have, I don't see hands. Maybe there are some hands, but I don't see them. Well, if you don't have more questions, then let's thank speaker for very nice presentation.
Thank you.
Thank you very much.
Thank you very much.
Thank you, Professor Muravnik, for giving us this talk, and thanks to everyone who attended the seminar, and see you in 2 weeks.